Yes, the sizing of bearing on the basis of bearing rating life L10 is only valid if the load over bearing is constant and the bearing is running in full film lubrication condition. But if the load over bearing is uncertain like shock loading or vibrational loading, or if the bearing is not running in full film lubrication condition, bearing is running in boundary or mixed lubrication condition, then instead of bearing rating life L10, we have to make sure bearing static safety factor S0 according to loading uncertainty level. And in this video, we will mainly focus on sizing of bearing in case of uncertain loading like shock loading or vibrational loading. Plus, if the bearing is running in boundary or mixed lubrication condition. Because I had already explained bearing sizing on the basis of bearing rating life L10 in case of constant loading and when bearing is running in full film lubrication condition in this video in too much detail. Link is in description. So if you are new here, you can watch this video later on. So here the loading behaviors like constant loading, shock loading or vibrational loading are self-explanatory with their name. But what about lubrication condition? When we can say bearing is running in full lubrication and when we can say bearing is running in boundary lubrication or mixed lubrication. So if the lubricant inside the bearing makes a thin but full film lubrication between bearing rolling elements and the bearing raceway and avoid the direct metal to metal contact when bearing get into running condition, means no metallic friction. This is considered as bearing full film lubrication condition. But if the lubricant inside the bearing doesn't make full film lubrication layer and as a result rolling elements make direct contact with the bearing raceway in running condition, and then metallic frictions happen, and this lubrication condition considered as boundary lubrication. And if the lubricant make full film lubrication at constant loading and also make boundary lubrication for short period of time when bearing goes into peak loading, then we call it mixed lubrication condition. And the formation of these lubrication condition inside the bearing is depending on many factors. Mainly on viscosity of lubricant, amount of applied load and speed of the bearing. So how we can predict the lubrication condition for a selected lubricant inside the bearing at certain load and speed of the bearing? Because knowing the lubrication condition inside the bearing is very important because bearing sizing process is something like this. At very first, the first step is knowing the bearing lubrication condition. If the bearing is running in full film lubrication, then we have to do the sizing of bearing on the basis of bearing rating life L10. And if the bearing is running in boundary lubrication condition, then we have to do the sizing of bearing on the basis of bearing static safety factor S0. And if the bearing is running in mixed lubrication condition, then at constant loading, we have to do the sizing of bearing on the basis of bearing rating life L10. But we have to also make sure the bearing's static safety factor S0 for the peak loading conditions. And if we have to do the sizing of bearing on the basis of bearing static safety factor S0, then the second step is choosing the recommended safety factor S0 value as per the loading behavior, as per the loading uncertainty level. Higher uncertainty level means higher factor of safety. And our selected size of bearing should meet or exceed the recommended static safety factor S0, which we will learn with example later in this video. So how to predict the lubrication condition in the first place? So there is a calculation basis, calculation of lubrication viscosity ratio, K. But first I want you to understand the basic concept of lubrication conditions. So at the very first, when bearing is not moving, bearing is stationary. Bearing rolling elements make direct contact with the bearing raceway, means pure boundary lubrication, no matter how much lubricant is inside the bearing. And when bearings start rotating, after certain speed, generally after 10 rpm, lubricant start making a thin layer around the bearing rolling element and the bearing raceway, and we call it mixed lubrication condition. And when the bearing reaches a certain speed, lubricant successfully establishes a full film lubrication. But in case of sudden loading or vibrational loading applied on the bearing, full film lubrication layer may be get broken, but can be restored again when peak load is removed. But how thin a full film lubrication will be formed or maybe not sufficiently formed will depends on the applied load over the bearing, speed of the bearing, amount of the lubricant inside the bearing, and viscosity of the lubricant. So this is the concept of lubrication condition, and the calculation basis of lubrication condition is the calculation of lubrication viscosity ratio K. If the viscosity ratio K is more than 4, it indicates full film lubrication inside the bearing. If the viscosity ratio K is less than 0.1, it indicates boundary lubrication. And if viscosity ratio is between 0.1 to 4, means mixed lubrication condition. We will learn calculation of viscosity ratio with example later in this video. But before any calculations, let's start from the concept of bearing sizing one more time, and this time even deeper. So the concept of bearing sizing is directly based on cause of bearing failure. Means the size of bearing should be sufficient to ensure that bearing won't fail for a given load and the speed. And bearing can be failed because of many reasons, like insufficient lubrication or containment inside the bearing. Or bearing can be thermally seized when overspeeding of the bearing, because a high temperature will reach inside the bearing after bearing cross the reference speed limit. Bearing can be also fail if we will run the bearing at the load below minimum requisite load, because the rolling elements may start sliding instead of rolling, and as a result high friction, high temperature will be generated and bearing will be fail. Or the bearing other components like seal or cage of the balls can be also fail and will be considered as bearing failure. But none of these failures are directly related to the bearing sizing. It means these failures can be occurs even if bearing size is sufficient, because these failures are related to operating environment of the bearing, like insufficient lubrication inside the bearing, or the bearing fitment, like insufficient tightness or looseness of the shaft inside the bearing. The bearing sizing is related to only two main failures. First is permanent deformation of the bearing elements, and the second is fatigue failure of the bearing in long run. Means the bearing size should be sufficient to ensure that bearing won't be failed because of these two main reasons at given load and the speed. So when we apply a certain load over the bearing, bearing elements goes under stress. And if the size of bearing will be relatively small, bearing elements will get permanently deformed, like flatten of a rolling element. Therefore, the size of bearing should be sufficiently large enough that could not be deformed under the applied load, under the applied given load. But here is the thing, if bearing cannot get permanently deformed under applied given load, then it doesn't mean that bearing will never fail. Bearing could be fail in long run because of bearing's fatigue failure, second main reason of bearing failure. Because when we run the bearings at certain speed, every component of the bearing goes under cyclic load, and if any metal goes under cyclic load for a long period of time, the metal could be potentially fail because of fatigue failure. And in case of bearing, rolling contact fatigue failure, RCF failure, either on bearing elements or the bearing raceway. If the fatigue failure occurs on bearing elements or the raceway, a metallic crack propagation start and bearing start compromising their function, like increasing in friction and decreasing in bearing running accuracy. So the bearing size should be sufficiently well enough that which cannot be get permanently deformed, but also cannot be failed because of RCF failure for a desired or recommended number of revolution, or we can say a recommended period of time at a given speed and under given load. And to verify the sufficient size of bearing, we use bearing rating life L10 formula, which ensures that bearing will deliver the recommended life before first sign of fatigue failure. For example, if the bearing rating life L10 of the selected size of bearing is 5 at a given load, it means the selected size of bearing ensures that the bearing will run for at least 5 million revolutions without getting permanently deformed, as well as without getting failed because of fatigue failure before 5 million revolutions under a given applied load. If the selected size of bearing rating life L10 is shorter according to recommended life of bearing for a particular application, then we should go for the larger bearing size. And if the selected size of bearing rating life L10 is too much, then we should go for the smaller size of bearing to optimize the cost of bearing. Because sizing of bearing means selection of economical and smallest size of bearing which can run for recommended period of time as per the application. Bearing should not be too large and too small. It just should be as per the recommended life. For in-depth bearing rating life L10 calculation and bearing recommended life, you can watch this video. But here we have to understand a very important thing, that the bearing rating life L10 ensure the bearing fatigue failure only if the bearing is running in full film lubrication condition. Means we can predict the fatigue failure event only if the bearing is running in full film lubrication, which means no metallic contact, no metallic friction within the bearing. But in case lubricant cannot make full film lubrication, then metal to metal contact will be happen, means metallic friction will be happen. And eventually before fatigue failure, bearing will be failed because of metallic friction. Then there is no benefit of predicting fatigue failure bearing rating life L10 calculation. Moreover, by definition, fatigue failure of a metal is when metal goes under cyclic load, not goes under frictions. We are able to calculate bearing fatigue failure with 90% accuracy only because rolling elements are the keep separated from bearing raceway with a thin layer of lubricant and do not make any metal to metal contact, do not do the frictional contact, only apply cyclic load. But if metal to metal contacts happen, then bearing rating life formula L10, which is actually a fatigue failure calculation formula, will not give you the exact result. The actual result will be different from the calculated result. So if we cannot make sure the bearing fatigue failure, then we should at least make sure that bearing will never goes under permanent deformation in any circumstances. And to do that, we have to make sure the bearing static safety factor S0 as per the loading uncertainty level. So what is the bearing static safety factor? So we can say the bearing static safety factor is a measure of safety margin of the bearing under static load. It is defined as the ratio of minimum load that causes a permanent deformation of the bearing to the actual equivalent applied load, where the minimum load that causes a permanent deformation is the bearing basic static load rating C0 and the applied equivalent load is P0. To be exact, the bearing static load rating C0 is defined in ISO 76 as the load that results in certain value of contact stress at a center of contact of most heavily loaded rolling element or raceway. The contact stress value are 4600 megapascal for self-aligning ball bearing, 4200 megapascal for all other ball bearings, and 400 megapascal for all roller bearings. These stress values produce a total permanent deformation of the rolling element and the raceway that is approximately 0.0001 of the rolling element diameter. And the load are pure radial for radial bearing and and axial centrally acting on thrust bearing. And you can find this value in bearing datasheet, like here for bearing 6205, a static load rating C naught is 7.8 kilonewton. Whereas C is the bearing basic dynamic load rating, which is defined as the load at which bearing runs for at least 1 million revolution before first sign of fatigue failure. And that's the difference. Basic dynamic load rating C is related to bearing fatigue failure, and we use in bearing rating life L10 formula. Whereas bearing basic static load rating C naught is related to permanent deformation of the bearing, and we use it in bearing static load safety factor formula. In other words, we can say a static safety factor S naught represents that how much bearing is stronger as compared to maximum load it is expected to support without permanent deformation. And you can see this is the recommended safety factor table from SKF bearing, and represents that how much times bearing should be stronger as compared to maximum load as per the loading uncertainty level and the type of motion. Like for high certainty means low uncertainty means when we are pretty much aware of the load and if the motion is continuous, and if a permanent deformation is acceptable, then you have to maintain only 0.5 times of the safety factor. And if a little deformation is acceptable, then the safety factor should be 1. But if you don't want any deformation, then you have to make sure the selected size of bearing safety factor should be 2 times. And if the loading uncertainty level is high, means low uncertainty, like road vehicles, load is completely uncertain, then you have to consider extra safety factor. And after choosing the right static safety factor, we can calculate required bearing basic static load rating C naught. And on the basis of bearing basic static load rating C naught, we can select the required size of bearing. So let's do it with a calculation example. So let's say this is a slow moving cam and floor application. A gear motor is rotating this cam at only 5 rpm. And this cam is supported with a ball bearing, and this floor is supported by LM guide and the block. And because the loading on cam bearing is pure radial, so I have to use a deep groove ball bearing, and I have used 6205 as per the bearing shaft diameter 25 mm. So when this cam start pushing this floor up, a sudden load applied on cam bearing, let's say 500 kg. So I have to make sure that bearing size 6205 is well enough or not. So in this application, the applied load is pure radial 500 kg. So the equivalent load P equation will be simplified to P equal to Fr, means 500 kg, 4.9 kilonewton. More about equivalent load calculations in this video. So if we will try to calculate bearing rating life L10, then basic dynamic load rating C, which is 14.8 kilonewton of the bearing 6205, divided by equivalent load, which is 4.9 kilonewton, and exponent P, which will be considered 3 in case of ball bearing, L10 will become 25.9, means 25.9 million revolution, which seems very less, but in operating hours it will become 86,447 hours. Because speed is only 5 rpm, the consumption of bearing cycle is very slow, and this rating life is okay as per the recommended life of the bearing. But this is not okay. Bearing will fail far before reaching this calculated bearing rating life L10. Because this calculated rating life L10 ensures the bearing failure based on fatigue failure, RCF failure, only in case of full film lubrication condition. But here the speed is only 5 rpm, which would be considered as slow speed. The speed less than 10 rpm is considered as slow speed. And at very slow speed, full film lubrication cannot be formed. It means this is the case of boundary lubrication. Means in this situation, bearing rating life L10 is not valid. But we should make sure on the calculation basis. Calculation of lubrication viscosity ratio K, which is equal to V actual operating viscosity of oil or grease-based oil divided by V1 rated viscosity, which is function of mean diameter of the bearing and rotational speed. So how to calculate V and V1? So the actual operating viscosity V of the lubricant is determined at operating temperature. And we can refer this table from SKF. I will leave all this table in description. So here the ISO grade of lubrication oil or oil-based grease like hydraulic oil 46, 68, 100 are given. And these are kinematic viscosity of this lubricant at operating temperature. So let's suppose the operating temperature of the bearing is 70 degree, which is kind of normal temperature for a bearing. And we are using hydraulic oil 68 as lubricant. So the viscosity of hydraulic oil 68 at 70 degree centigrade is around 22 mm square per second. And for exact value, you can download the data sheet of the lubricant. So here the kinematics viscosity at 45 degrees C is 68 mm square per second. And in this table also, viscosity of oil 68 at 45 degrees C is around 68. So at 70 degrees centigrade, let's say it's 22 mm square per second. And now the rated viscosity V1. So the rated viscosity is a function of bearing mean diameter and the rotational speed. And for rated viscosity, we can refer this table, or you can also use online tools like SKF bearing selection tool. So in this table on x-axis, bearing mean diameter is plotted, and on these lines bearing speed are plotted. And accordingly, rated viscosity V1 is defined on y-axis. So we have to calculate mean diameter of the bearing. So the mean diameter of bearing is equal to bearing OD plus bearing ID divided by 2. So for bearing 6205, mean diameter will become 38.5 mm. So in this table, our bearing speed is only 5 rpm, means this line, and the bearing mean diameter 38.5 mm will be somewhere around here. So the rated viscosity V1 would be more than 1000 mm square per second. So let's consider the 1000. So put the values and viscosity ratio K will become 0.02, means less than 0.1, means full film lubrication is not possible. Boundary lubrication will be there. Even if you change the lubricant, let's say this ISO grade lubricant 1000, then at 70 degrees centigrade, actual viscosity would be 200 and viscosity ratio K will become 0.2. which indicates kind of mixed lubrication condition, but cannot be full film lubrication. For full film lubrication, the K value should be 4 or above. Because the main reason of low viscosity ratio K in this case is the rated viscosity ratio is too much. Because speed is so slow, it's only 5 rpm. And this is why for low speed applications, bearing a static safety factor S0 calculation is must. So this is case of boundary lubrication. So we have to make sure the static safety factor of the bearing as per the uncertainty level of the loading. So in this table for shock loading, and if we don't want any permanent deformation, then our safety factor S0 should be more than 2. So in this equation, we have S0 2. We have applied load 500 kg, 4.9 kilonewton, means the required basic static load rating C0 of the bearing is equal to S0 into P0, 9.8 kilonewton. Means our selected bearing basic static load rating C0 should be at least 9.8 kilonewton. And our selected bearing 6205 basic static load rating C0 is only 7.9 kilonewton, Means we have to go for the larger size of bearing. So let's select 6206. Basic static load rating C0 is 11.5 kilonewton, which is fine as per our application. So this is it for this bearing sizing. I know this video was long, and also I have used just one or two, three formulas, and you can find this formula in or everywhere on internet or any textbook. But you will not understand all the little concept of the mechanical engineering, which actually makes us a better design engineers. But always remember, these all calculations like bearing rating life or a static safety factor are only valid for the steel bearing, hardened steel bearing. For other materials bearings like ceramic bearing or plastic bearings, these formula would be not completely valid. We have to completely rely on the manufacturer data sheet. In next video, we will learn how to calculate the bearing shaft and housing interference fit. So next video should be on your screen, or you can check the description. And thank you so much for the watching.